Welcome to another episode of AI with Sally, an EE Times podcast that brings you inside my conversations with luminaries of the AI chip industry. In this episode, we're joined by Brandon Lucia, CEO of Efficient Computer. Efficient Computer launched its Electron E1 Edge chip last summer based on years of research from Carnegie Mellon. The company's developed a reconfigurable spatial Dataflow fabric it uses in place of a CPU or an accelerator, and the company's claims say it can offer massive, orders of magnitude energy savings on CPU, DSP, and AI code. If you're as intrigued by this as I was, you're going to love this conversation with Brandon Lucia. Here's my conversation with Brandon. Welcome to the show, Brandon.
Yeah, thank you very much for having me, Sally. I'm excited to be here and talk to you about Efficient.
So it seems like Efficient, you've designed a type of accelerator or a type of processor, really, that's incredibly power efficient, hence the name. But using completely new concept you've invented called Reconfigurable Spatial Dataflow Fabric. And I think in the world of AI accelerators, we're probably familiar with the idea of reconfigurability and the Dataflow architecture, certainly. But I'm very curious about how you're applying this in a kind of sensor edge scale of product and about how and why you say this is good, kind of beyond AI for all different kinds of workloads. Um, if you don't mind, maybe we can just start by talking a bit about this fabric, what it is and how it works. Maybe you could just tell us a story of how you came up with this idea for this fabric and how it works.
Yeah, sure thing. So the story of the fabric goes back to its humble beginnings as a research project at Carnegie Mellon. I'm Professor Carnegie Mellon, co-founders Nathan Beckman and Graham Gobieski. We worked together back at CMU. It feels like forever ago. It was 10 years ago or something that we started working on this. And where it started, actually, I mean, this is a fun way to think about, how far we've come with this. We started by looking at the problem of why are general purpose CPUs just inefficient, and this was before there were such thing as commercially available accelerators. And so we studied that problem for a year. It was kind of data collection mode, understanding, looking at all the studies on that had been done before, and what we found was there's some really basic, fundamental overheads that are built into the von Neumann CPU model. And we started chasing those down, and the further we went, the more it became clear that we need to do something radically different from the von Neumann CPU architecture. So we did that. We developed a Dataflow architecture. We sort of operationalized our conclusions from that study. And what that meant was, there's a couple of things that are really simple you can get rid of. So one of the things that costs a lot of energy in a CPU is every cycle, so like 1 billion times per second-ish, you're going and getting a new instruction. And that's very expensive because you have to move the instruction from a memory that sits next to the CPU execution pipeline. And then once you get the instruction inside the CPU pipeline, you have to decode it, figure out what it's doing. Is this addition or multiplication or whatever? And then you have to reconfigure a bunch of internal circuitry in your CPU pipeline so you can actually run the operation. And all that's very expensive. And so that's kind of the front end overhead that you have to deal with in a CPU. That's like shorthand for that, is front end overhead. Another thing you have to deal with is when you do an operation, you have to pull, if you're adding two numbers together, right? You have to go and get the two numbers you want to add together. And so that's very expensive as well. And you don't really get those from a memory sitting nearby your processor. It could be the register file, or it could be some other memory. But regardless of which memory it is, that's multiple memory accesses, and they're indirect because you pull the values out and then you do the operation, and then guess what happens in the next cycle? Well, you put the value back into that register file, and you do the same thing again. And again, it's 1 billion times per second. So those are some examples. I mean, that's not the whole list. That's just my favorite ones to talk about. Those are some things that we saw where we were like, this is really basic stuff that if we can get rid of it, will save a lot of energy. So we took a completely different approach, and I can tell you a lot more about the details of how we did that, microarchitecture and so forth.
Absolutely. Yeah. I think so. People that listen to this are obviously AI accelerator and kind of NPU experts. So you're using some words like reconfigurability and spatial data flow that we're very used to hearing in AI accelerators. But do you want to go through reconfigurability or spatial data flow first? I guess they don't really make sense without each other, right?
Yeah. So we got rid of those front end overheads and the data movement overhead that I was just talking about, and we did that by developing our spatial data flow architecture. So one way of thinking about this, and this is going to sound a little new agey, but a CPU thinks about computation in time, and we think about a computation in space. And so that actually has a very specific technical meaning. It literally is true. That's what we're doing. In a CPU, you have one set of execution resources, which is your execution pipeline, and your time multiplexing. For each different instruction in the program, you're switching up what that one set of resources is doing. Now, it's not actually only one, but for the purpose of explaining this, it's good enough to say that it's one. In our architecture, we have a big array, like a spatial array of what we call tiles, and each one of them it's like less than a processor core. It doesn't have the von Neumann sequencing logic. It doesn't have a program counter of its own. What we do is we have done hardware software co-design. So we have a compiler that understands our architecture, and our architecture exposes a reasonable interface to the compiler. And so the compiler can digest plain old code like C, C++, Rust is something that a lot of our customers have been asking for. And then, things like the AI frameworks like, PyTorch and Onyx, all the stuff you'd expect. We can digest that into a set of instructions that we can spatially array across the tiles in our architecture. So picture a square array of tiles. And now on each of those, there's a different instruction from the program, like ISA instruction from the program. And one of the things that's unique about our architecture, especially when you put it in contrast to the CPU, you can see how this is unique. We encode the communication between program instructions directly in the ISA, in the architecture itself. And so when the compiler puts the instructions down on the tiles, it also essentially wires up a route from one instruction to the next one. And that happens on a program dependent basis. So in one program, you might add two numbers together and then multiply the result with another number. And so you could put those instructions down and wire up the results so that they go to the right place. And that's really powerful because you put the instructions down once and they stay put for a long time. So you're not doing any of this fetch, decode, reconfigure stuff over and over and over again. They just stay there. Your tile that's doing add and your tile that's doing multiply, they keep doing that for a long time. So this is the sort of spatially arranging your instructions rather than time multiplexing aggressively. And then the data flow part is how the operations communicate through those wired up connections. We have a very efficient on-chip network. That's part of our secret sauce. We have a very efficient way of communicating between tiles. It's literally almost like just wires that are configurable between the tiles, it's so cool. That's like approaching, how close can you get to the physical limit of efficiency for data communication? It's wires. And so that's part of our implementation is that, and we can take the instructions and their communication pattern. That's what we call a data flow graph. Let's sort of throw more jargon at you here, but we take that and we map the data flow graph onto the spatial array of tiles, wire up the connections, and then set it running. And it will just start running for, millions of cycles. And when it's done, the fabric can reconfigure itself and go get the next piece of your computation, like the next loop nest or the next layer of your network or whatever. And that's how computation progresses. It's fully general purpose. We support, you know, all the AI favorites, convolution and matrix multiply and all that stuff. But we also do very weird stuff like irregular graph search and sorting and all the kind of classic textbook algorithms that those don't map onto GPUs and hardware accelerators at all. But those are simple for us. We map those onto our hardware, and we see big dividends actually paid off for those types of applications. Which, by the way, that's computation that's pervasive in systems that are using AI. They're also using all those other algorithms all the time. It's not just convolution. So,
Yeah.
so that's some details about our architecture: hardware, software, co-design, spatial data flow. That's how we do what we're doing, and we get huge benefits. It's like an order of magnitude improvements in energy.
Okay, so on the configurability element, I heard what you're saying about the wires and the connectivity between the different compute tiles is configurable. Um, Within the compute tiles, how fixed are the operations that each of those tiles can do? Do you configure that as well every time, or are those more fixed? Like, do you have a block of adders and a block of multipliers and you route between them or something? Like, tell me about the granularity of reconfigurability.
Yeah, great question. So when we take an application, like I said, we turn it into a data flow graph, right? And so that means it's a sort of abstract construct swirling in space where You have instructions, and those are the sort of abstract blobby things floating in space, and there are like wires connecting the instructions together. When we put one of those abstract blobby instructions down on a tile, that tile gets configured at that time to take on the personality of that instruction. So inside of a tile, we have, an ALU. It's more than that, but that's a simple way of saying it. It's basically an ALU. That's a simplification of what we're actually doing. And so when you put an instruction down, you can say, okay, this tile is going to be doing an add, and the output of the add is going to get routed onto, some other tile that's doing multiply or doing load or something like that. In practice, I mean, I'm not going to go into the full, 2 hour 2 hour lecture on this, but there's a lot to say. The details are very cool, and I love what we've come up with. It's amazing what the team has been able to develop in the last few years since we've been doing this. But we're we're able to pack a lot of instructions into a single tile by fusing them together. So we have, it's not just an ALU. We have a lot of functional logic, and so we can take multiple instructions that are compatible for the set of resources that we have inside of a tile and kind of squish them together into a little, in the language of digital logic design, it's a combinational block, which basically just means that it all executes in a single cycle. So it's a whole bunch of operations, and they all run as a single unit in a single cycle. And that's configurable. That's one of the really cool things about this is by doing that operator fusion, we get very high instruction density across the fabric. And you're doing essentially more instructions per cycle per tile. So, looking at contrast to CPUs, you might get 2 instructions per cycle. I'm choosing randomly, but that's not far off from what you'd expect to get in a CPU, right? There's optimizations to get more, but that's sort of a typical number, especially in the category that we're operating in. On our fabric, we have a 12 by 12 array of tiles, and that's flexible. This is our implementation today is a 12 by 12 array. And there is an operator fusion happening, like I was just describing a second ago. And so on a given cycle, we may have several hundred instructions executing per cycle because of the nature of the data flow graph and how we can spatially distribute it. And so now you can begin to see from that how we get this massive boost in efficiency. So in one sense, like time is efficiency, just go faster and be done with the computation. That's a great way to reduce energy because time times power is energy. So if you take time down, even if it's exactly the same power, then you just save energy. It's like you're doing a very good thing to save energy that way. But we're also decreasing the power of the operations too, because of the efficiencies I described around not time multiplexing and doing a lot of reconfiguration and not doing indirect data movement. So, the power of activating a tile to do its work is also less. So we get it's a disproportionate, energy win for the amount of resources that we've allocated into the hardware. So that's where the efficiency gains really come from is from all that. And when we compare to a lot of in-market parts, we look at the most energy efficient general purpose processor that was in the market before we entered the market. And if we see that it's only 5x, that we've only improved on that by 5x, we think there's something wrong and we keep digging.
Okay.
We regularly see an
Aggressive.
order of magnitude. Yeah, regularly
Okay.
see an order of magnitude. Yep.
Um, okay, kind of excited thinking about fusing all these operations together and so on. But it's just, I understand the efficiency gains, but to clarify, this isn't a VLIW architecture, is it?
Oh, that is a great question. Okay, so the history of VLIW
Okay.
goes back goes back a long way. VLIW and Dataflow have since like the 1980s when people were talking about these for the first time. Dataflow was first uttered in the academic research in like 1979. Jack Dennis at MIT, came up with the foundational principles, and Arvind at MIT went on and developed these ideas. And then there was a proliferation, the TRIPS project. There's a whole history we could get into, and I just kind of did right there. But VLIW is kind of a companion to that. So VLIW is like, how can you take the CPU and preserve most of the von Neumann apparatus, where you have this sort of sequencing forward in time of, in the VLIW case, groups of instructions instead of like one instruction at a time or two instructions at a time, and putting more of the scheduling into the compiler, making it more statically scheduled. And that is something that we actually share with a VLIW design. So you were clearly paying attention. You noticed that we're statically scheduling all these operations. And so isn't this really just a massive, massive VLIW? That is one abstraction that you could use to look at it. Now, we are not a VLIW processor. That's just sort of an analogy to help understand the concept. We're doing a lot more instructions. We eliminate a lot of the fundamental problems you have that they basically emerge from combining von Neumann with Dataflow and the way that VLIW attempted to do that. So you know, many things come up. One is that you typically have this narrow scope for bundling instructions together, and that presents a challenge to the compiler when you're restricted to only being able to schedule like 4 instructions at a time. And so that made the compilers for VLIW really hard. What we've concluded in looking back over the history of computing is that um, we we were we were more aggressive in co-designing the hardware with the software. VLIW said, let's preserve most of the hardware, let's preserve most of the software, and then let's make these tweaks. But the tweaks actually made it very difficult because you're living in the confines of something that looks like von Neumann. We said the architecture is what it should be, and the compiler is what it should be to meet the architecture in the middle between hardware and software. And so what we got was something that was much greater than what VLIW could deliver. In fact, when we look at our design and we compare, I've been talking about CPUs. If you look at the other end of the spectrum and you compare to accelerators, fixed function accelerators that only do one thing, we're competitive with some accelerators in the market. Now, if you're doing matrix multiply and you do a fixed function circuit to do matrix multiply, that's always going to win. That's physics. You can't beat that. But there are accelerators for things like, DSP, where they're highly specialized. That's all they do. And we're able to meet or exceed their performance and improve on their efficiency because of our architecture. And that's without giving up on the generality. We can also go and run Doom. Literally, we have run Doom on our chip because, of course, we run Doom on our chip.
Um, yeah, I think when I hear somebody say, "Oh, we've got this kind of general purpose accelerator," or "We've got something that can do general purpose compute faster than anything else," um, I hope you'll forgive me for coming with a little skepticism. I'm very used to the idea that you trade off flexibility with performance. So, uh, are you somewhere on the flexibility versus performance trade off, or are you just playing by some other set of rules?
Uh, you're asking two questions. So one
Okay.
is, yes, we're playing by another set of rules. We've changed the paradigm substantially, and by doing that, we escape the sort of the existing Pareto frontier. So one way of thinking about it is we've actually shifted what the Pareto frontier can be. So the trade-off space is just different when you look at flexibility um, uh, uh, versus efficiency. And so that's one thing that's one thing that's highly differentiating for us is we've moved that frontier, and so we're actually not giving up. We're at the knee in the Pareto curve, so sort of somewhere in the middle. We're not at the sort of CPU level of cycle to cycle reconfigurability. We're not at the accelerator level of fixed function logic, but we have tuned the architecture at that point so that we capture the full behavior of general purpose languages like C and C++. So what that tells us, and this is the other part of the answer to your question, is like what that tells us is the CPUs have been over designed for that kind of flexibility. There's more flexibility than you need to support general purpose programming languages. And the proof, I'll hold this up for you, this board with our chip on it, this is our Electron E1 evaluation kit. And you can see the chip in the middle. We run general purpose programming languages on this board, and we take direct full system from silicon energy measurements, and we compare to our best competitors in the market. And we spend actually something that I'm proud of my team for doing is we spend a lot of time optimizing for the other guy to make sure that our comparisons are really fair. So, this isn't modeled. This isn't like we're fluffing numbers so that it sounds, oh my God, amazing. It's like we have on the other side of that wall over there, we have a shop where we're doing measurements every day to validate these kinds of claims that we're making. Um, there's a trade-off space that we're playing in, and I can talk more about that if you're interested too.
Sure. Yeah, yeah, please.
Yeah. So one of the things that we've done is we've, like I said, moved the Pareto frontier on flexibility and energy efficiency. There's also an area component to that. So if you compare to a CPU can be very compact. And it might be intuitive why, given how I described our architecture. A CPU has like one functional unit and a little bit of sequencing logic around it. And so it's inefficient, it's slow, there's low parallelism, and it doesn't do very much. per cycle. But okay, it's very small. That's a virtue in applications where you really care about squeezing that little bit of uh, little bit of area. That's the primary optimization goal. And so we trade. It's not like linear in the amount of tiles that we have. It's much better than that actually. So a small factor, depending on what you're comparing to, a small factor of area for a disproportionately large factor of energy efficiency and performance. And so that's the trade-off that we're making. And it is one that is, you can think of it as directly corresponding to parallelism in the design. We're eliminating all of the expensive sequencing logic, which is very power hungry and area intensive. We're dispensing with that. A lot of that is actually in the compiler where we do static scheduling in the way that I described before. And the benefit is that we can then go and recoup that area, fill it with functional logic, and we get something that, again, like I said, it's larger than the most hyper optimized for area CPU out there. But we have this disproportionate win in performance and energy efficiency. In some sense, that's a similar bargain to what you see with AI accelerators. If you take a matrix multiply and you want to do it efficiently, you need to map it in parallel across an array of hardware resources. Um, that bargain is to say, give up on any sequencing logic. Don't do any scheduling or any reconfigurability. Just do matmul. And if your business is transformers, then hooray, you've succeeded. That's good. But what we found when we talk to our customers is there really is a need to support all the rest of computation in general, especially in physical AI, where it's not just running transformers day in and day out. It's not just running convnets. It's also doing DSP. I mentioned graph search. That comes from a real customer use case where they needed that to work well. And they were like, please help. It doesn't even work on our GPU. What can we do with this? So those workloads, those other components of AI systems, especially in the world of physical AI, which is what we're targeting with our Electron E1 product, those are very important, and they're neglected by accelerator-based architectures and largely by GPU architectures as well. But we step in and we support them really well with our Electron E1 silicon.
We're gonna come to the Electron E1 in a second, but maybe just one more question with that I'm having trouble getting my head around, which is the way that you statically schedule for CPU code where there are branches and loops. Obviously, with AI acceleration, we used to talk about AI inference on this show where it's the same algorithm every time, and it's kind of, it just works through all the different operations kind of one after the other. If I have CPU code where I'm looping and I have branches and I have ifs and so on, how do I schedule for that at compile time?
hmm Yeah, this is one of the most common questions that I get when I talk about how do you talk about the spatial architecture. How do you deal with control flow? And that was one of the fundamental problems that we solved in the research. So I think I started telling you the chronology of our company, and I started it by saying we were at CMU and we started developing this architecture. One of the big problems that we ran into was exactly this. How do you support irregular loops, if going beyond, parallelizable for loops? Those are easy. You can just map them in parallel and everything just kind of runs. And that's basically what the matmul accelerators are doing. They're kind of just unrolling the loop as much as possible, and it's perfect for the hardware. So when you get irregular loops, you can't do that. And so irregular loops can be with early termination conditions, or think of like a while loop. You don't even know how many iterations it's going to run for. You might have conditional logic around it or whatever. It doesn't matter what the structure is. We convert those to data flow. So that's a strange thing to think about because normally control flow and data flow are like the two sides of how your program executes. We came up with primitives that we invented these in the research years ago, and they are ways of taking arbitrary general purpose control flow constructs and mapping them into selective data flow constructs. Selective meaning, one way of solving the problem is take your if, execute both sides of the if and produce both results. That's a little bit expensive, but people have done that in the past. And then use the output condition from the if itself and pick which of those results you want to use. And that's something you can do. That's called predication. It's existed for a long time. In fact, VLIW machines used predication heavily. It's just a bit expensive because you have to run both sides of your conditional statement. And there's an analogous thing for loops where it's just a bit challenging to map to that idiom. But what we did is we came up with a lightweight construct that allows us to selectively execute only one side of a conditional control flow construct, and we can do it without paying that that predication tax. Um, the cartoon version of it is essentially you evaluate the condition of your loop of your if statement, and then you steer the value down one or the other switch track of the train tracks that's moving your data through the architecture.
Wow. Okay. Thank you for the cartoon version.
Yeah,
I like that idea a
sure.
lot. Um, okay, so it's really compiler heavy. A lot of your secret sauce has to be in this incredible compiler that you've been building. Um, can you tell me anything about what stage of maturity you're at with that? I mean, I think a lot of AI hardware startups kind of learn this the hard way. Compilers obviously super critical. How long have you been working on this compiler and it works, right?
Oh, yeah, yeah, yeah. If we had more time today, I would alt tab over and I would show you our compiler in action.
Okay, another
Doom
time.
is yeah, Doom is one of my favorite things to go and build with our software stack. But let me tell you the story of our compiler. We have been developing this, the concepts underlying our compiler. We've been developing since about 2017. And the implementation that we have now, we've been working on for the last roughly 5 years. And it is highly robust. We had a compiler before we had a single line of hardware design code. And so we've heard repeatedly from my closest mentors and people whose opinions I really respect in the chip world. Um, we've heard that idea that, a company that makes a new silicon product that is, even if it's amazing what it can deliver, if you fail on the software stack, it's going to be a hard face plant with the customers that you try and attract. And we've now seen the benefit of being prepared in this area. We're able to take our compiler and we have, a web-based playground that early evaluation customers can go to, and they can put in some C code, put in some arbitrary code, and we have a web-based simulated execution environment where they can see it running on the Dataflow. And it's actually running our compiler. That's not like demoware. That's actually booting up a Docker container somewhere in the cloud and running our compiler. I mean, the fact is our customers are using our compiler to compile, thousands of lines of code every day for their applications. And that includes, like I said before, C and C++, Rust support, coming online at the end of this quarter. We have support for the AI frameworks that everyone's using. It's quite robust. Now, I would never say it's perfect. Software is the art of software is the art of evolution over time. It's malleable, and we'll continue to improve it with time. But what we have right now is something that I'm, really proud of the team for having pulled together and to have delivered to our customers in our latest release.
So let's talk about the E1, which is the chip that you've built based on this concept. This is a sort of gigaops scale processor. In other words, it's right down at the microcontroller end of the scale. We touched on physical AI and your kind of suitability for physical AI applications earlier, but kind of broadly speaking, why does it make sense to go to the small end of the scale first? On this show, we talk about everything from data center accelerators right down to the microwatts. So why are you starting at one end, and why does it make sense to start at that end?
Yeah. So we thought very strategically about this. So our architecture, we know from the research side of things and from subsequent exploration, we know that our architecture is suitable for very small applications all the way up to, we envision uh, ways in which we could apply directly to the data center. Maybe someday. That's not what we're doing right now. We've tackled this physical AI market first, and the reason for that is twofold. On the one hand, it allowed us to really focus on a particular fabric implementation that didn't incur a lot of additional technical debt around complex interfaces and PHYs. We don't have to integrate like the latest, greatest high frequency ADC or memory interface or PCIe or Ethernet or pick your complicated thing that you would have to go and source and implement, and it's expensive. In addition to that, though, it's not just convenient for us. There's a really kind of fundamental thing that we saw in the applications in this space. When you get into physically constrained systems like you have in physical AI. So I like to think a lot about infrastructure observability devices, infrastructure monitors, industrial automation, the sort of low end of robotics, which goes hand in hand with industrial automation. things that fly and move on their own, which have a lot of sensors and actuators, things like that. Those are the applications where we just see this massive disproportionate benefit. And the reason is those are energy constrained applications. A lot of them live and die by the length of their battery. And so there's applications today that we're developing with customers where it's it's just not possible without the efficiency that we deliver. And by the way, those applications too, like I was saying before, they include a huge variety of different computations. So it's not just grind away and do 3 by 3 convolution all day, every day, forever. Some applications do some of that. But if you look further into what the broader application needs to do, it's just this wide variety of computation. So we see a benefit in our generality and the efficiency we deliver for that broad range of computational use cases. It basically allows those applications, those devices to exist at all. It's a capability that's not possible if you don't have this level of energy efficiency. The alternative is you use something less efficient, your battery dies in a couple weeks and you're just constantly swapping batteries, or even worse than that, you just engineer your application to be a conduit, like a thin conduit for data to the cloud, and then you're basically optimizing a, telco problem or something like that. It's sort of how little can you use your radio, and the device does no local intelligence, which you lose a lot of valuable insights that you can get if you do local intelligence.
Are we talking about microwatts, milliwatts? Like, I know you said, very, very long battery life, but I mean, always on would be kind of below a milliwatt for some applications. Where are you in the scale?
Yeah, so the Electron E1 is in the low single digit milliwatts. Depends on the use case, depends on the load. And so, yeah, if you want to take two AA batteries and you want to run for like 5 years, it's something like you have a couple hundred microwatt or something like that. I'm not doing the math in my head right now, but it's in that ballpark. And so with duty cycling, that is very achievable. We can meet or exceed that with a battery pack that, for these kinds of devices, they essentially disappear. And that's
Yeah.
the goal for a lot of these, especially you look at something like infrastructure. Infrastructure is something like I said, I love thinking about infrastructure applications. We have a huge footprint there in terms of our commercial traction now. Things like every utility pole, 350 million utility poles across the United States. And the way that those are addressed today for maintenance and for inspection is a guy in a truck pulls up to the pole and gets out and sort of taps on it with a stick and looks at it and tries to understand what the health of it is and assesses, is it leaning one way or is it leaning another way? Oh, does the transformer on top of the pole, does it look like it's sparking or does it have any hot spots or whatever? So that's like its typical inspection. Sometimes they'll have Cessnas go and fly the lines and they could see anything from above. That's insanely expensive. And it also, by the way, is the same way that it's been done since, I don't know, 1970 or something like that. Like it hasn't changed very much. And so you start to see like this huge footprint for AI to have an impact in the physical world. It's not just utility poles. There's millions of kilometers of like roadways and gas pipelines and the facilities that support all of those. So compressor sites that are extracting and compressing natural gas, and water infrastructure where you have water treatment plants and then water pipelines. All of this together is this enormous footprint for these kinds of devices. And up to this point in history, there has not been an efficient enough solution to put capability at a reasonable cost into those use cases, and then to run for a lifetime that makes the ROI make sense for the operator of this infrastructure. Today, because of what we have built, and Electron E1 is the first thing we're putting into the market to support these applications, we can do that now. This is a change in the way people can think about these applications, and that's very exciting. I know, like, okay, water pipeline is not generally the most exciting thing to talk about. Not for everyone. It's not like good dinner party conversation, but I love thinking about just the massive footprint and the amount of improvement you get from doing this. It's really amazing what you can get from the insights around this infrastructure, and it's stuff that every single person on Earth touches every single day.
Yeah. Um, okay. To clarify though, for the E1, this is an SoC. It's not a standalone accelerator. I don't need another host CPU or an application processor, or can you work that way as well if I wanted? Tell me about the kind of system level stuff.
Yeah. So for Electron E1, what we've done is built it as a standalone SoC. It includes for, I hate to even admit this, but it includes for boot and to handle some rare interrupts, which is just easier to deal with this way. It includes a very small, it's a risk, happens to be a RISC-V processor. We're not a RISC-V architecture. We're not, that's not part of our fabric architecture. But that allows us to do some, like I said, boot operations, manage some edge case interrupts, and mostly what happens is that after boot, control gets handed off to the fabric, and the fabric will run, self-reconfigure to the next portion of a program, self-reconfigure to the next portion of a program, maybe periodically tag the RISC-V to go and manage I/O devices or things that are infrequent and very low energy cost. And that's the typical operation of the system. We incorporated memory, and we have a complement of memory inside of the processor, 3 MB of SRAM and 4 MB of not-volatile memory, which is an amount for these applications where we can do pretty sophisticated on-device AI models. I mean, this is not like we're not running ChatGPT on these devices, but
No.
no, that's obviously not going to happen. But we can do very sophisticated AI tasks on audio data, on IMU sort of vibration and movement type data, and even on two-dimensional data sets like cameras. So we can take in camera data and we can manipulate that using DSP and analytics and AI algorithms as well.
But if I already know that I'm mostly gonna be doing AI inference, wouldn't I be better off picking something just with an AI accelerator, like just with an NPU, on it if I don't need also to do DSP code, for example?
Mm. Well, it depends. One thing that we've noticed is applications are not just convolution. That's just there's
Right.
not applications out there that only do that. And so what you're faced with is something that is so I'll go back to the research again. You're faced with something called Amdahl's law.
Yep,
And I don't know if you do you know this? Okay, yeah.
yep,
So Amdahl's law,
yep,
it
yep.
says, just to reiterate, it says you're bottlenecked by the part you can't optimize. And so if you're saying a lot of your application is, let's say that 90% of your application even is convolution, and you have an infinitely efficient accelerator, which by the way you don't. The best you can ever get out of that system relative to your baseline is a 10x improvement because you're stuck with that 10% at the end. And so the best you can ever do is eliminate the 90% that you could support on the accelerator, even if it was infinitely accelerable, which it isn't, by the way, then you're stuck with the 10%. And that is an effect that we see just pervasively across applications. There's this Amdahl's law bottleneck that really limits the benefit that you can get out of a system. So we support AI kernels. We support, things like, your convolution, matrix multiply, pick your favorite operator. We can go and run it on our fabric. No problem. We do it extremely efficiently. And then 100 cycles later, we also run the part that is the subject of the Amdahl's law bottleneck. And so that's why you don't want to use just a standalone accelerator glued onto like a, ARM core or something like that. Um, there's another thing to point out here, which is in a system with an ARM core and an accelerator, there is going to be a lot of back and forth between the ARM core and the accelerator. That's data movement, that's control signaling, and that can become a bottleneck as well. So data movement generally is the expensive part in a system. And so you want to pay a lot of attention in designing a system to minimize the cost of data movement. But if you are like explicitly designing your system to be segmented into CPU stuff that runs inefficiently and NPU stuff that runs amazingly efficiently, and you have to shuttle everything back and forth for it to work, it compromises on the efficiency gains that you get from the NPU. So that's like in addition to the Amdahl's law bottleneck, you now have this data movement overhead. So it's not it's there may be a use case out there where that's the best design. I would never say never. But overwhelmingly, what we see when we talk to customers is that there is this Amdahl's law problem, and you do need to be mindful of that kind of data movement issue as well.
So I understand you've made the E1 and you do sell this SoC, but I understand you also would license the IP if somebody was interested in that. Tell me about why that's the right business model for you or the right business model for you at this time.
Yeah. So our Electron E1 evaluation kits and chips are available now. Contact us, and we would love to talk to you about, getting these chips into your application and giving you the efficiency benefits for your general purpose code and your AI stuff. In addition to that, we are talking to right now the the potential lead customers for the Electron E1 Fabric IP. And this would avail a system that is today serving an application using, say, general purpose compute hardware like an ARM core, and provide a translation path from where they are today to migrating more and more capability to the fabric, demonstrating in an existing SoC to minimize the change for the customer the benefit of the fabric architecture. And so far, early days in that area of business, but we're seeing a lot of interest. We're tracking a lot of interest in, the benefits that we can deliver for a broad base of, general purpose applications, including AI. So one way to think about this from the perspective of the SoC designer, you have your ARM core and you have your DSP and you have your embedded GPU and you have your vector machine and you have your audio processor, and you have your renderer processor, and all of those are separate hardware modules that you integrate together. That's an abbreviated list. We've seen diagrams, system diagrams of real SoCs that are like 100 components all kind of glued together like little puzzle pieces stuck together. And that's what you need for full-fledged applications, just because there's such a diversity of different use cases. You need to have all of that. It's very expensive. Those SoCs tend to be incredibly large, huge team to verify and validate the design. So you're putting your design at risk by doing that level of integration. And you have all the data movement problems that I was describing before. And now you're bouncing things around between different components. In some cases, we've talked to people in the market who are using 4 or 5 different compilers to compile code for the same SoC. That is just a weird way of thinking about the world. I'm not accustomed to thinking about the world that way, where you have to run 4 different compilers to build your workload. We're a remedy to that. We simplify things. So you have a fabric, and it supports the broad range of everything from AI to DSP to arbitrary CPU code to anything you throw at us. There's an opportunity where if it were the case that you have this whiz bang NPU that really is infinitely good, we could maybe sit right next to it. Now, there is potentially a data movement cost there. Depending on how you design the system, we could potentially minimize that. But then you eliminate the Ondel's bottleneck because the fabric can support the general purpose components. And so there's a few different models. One is the fabric becomes the bulk of the SoC. Another is the fabric coexists in an ecosystem, a much smaller set of IP components that are required to integrate into the SoC. And so this business model exploits the strength of our architectural solution. We're not tied to a fabrication technology. We're not tied to a foundry. We're not tied to this node. Our technology is easily portable from one node to the next because our solution is architectural. And so it's not like we have to go and, redesign the standard cell to support the implementation of our technology. It's like we can take the sort of retail digital CMOS logic that you use to implement anything, and we can implement in that. If you have a node that is your favorite, there's nothing that prevents us from going and implementing our architecture with you in your SoC. So it's a big advantage for us in the market to be able to move around. And so that's to your question of, why is this the right business model? Because it taps into this unique strength of what we're doing.
All right, might be a bit early to ask this, but I'm going to ask anyway, which is what are you working on in terms of what's on your roadmap? Are you going to do a bigger chip? You're going to do a smaller chip? You're going to do a new generation of the architecture or the IP? What's on the roadmap, or what are you thinking about doing next?
So what I'm most excited about right now is seeing Electron E1 enter the market and deliver an order of magnitude improvement in efficiency
Okay.
for our lead customers. Now, I'm not going to announce any products at this point, but
Okay.
something that I love to think about personally is, what's the scalability limit of an architecture like ours? How far can we take this architecture to support more capable Physical AI applications. Again, not talking specifically about anything on the roadmap, but I like to think about, applications like mobility and bipedal robots and self-driving. And those are very exciting applications. And there's a huge footprint out there, commercial footprint, but also just impact to the world. If we can decrease the energy costs of these applications, think about what more we could do with that kind of technology. It's just amazing to think about that because there is so much happening and those areas are growing so quickly as we see these technology companies emerging and some bigger companies, changing direction to support these things. I think that it's a very exciting time to be looking squarely at the market that E1 is addressing, where we have just an incredible impact and a huge footprint across the range of devices and applications we support. But also looking forward, we're very excited to think about, with what kind of partnership could we demonstrate the scalability of our fabric architecture and software stack? So sorry to be a little cryptic, but I'm very excited about looking at those kinds of applications.
Not at all, but it is the perfect place to finish. Brandon, thank you so much. Wonderful conversations today, and we wish you all the best of luck.
Thank you very much, Sally. It was a pleasure to talk to you today.
That was amazing. Thank you so much, Brandon. If you want to learn more about Efficient Computer, check the links on the podcast page at eetimes.com. That brings us to the end of the episode. Please tune in again next time for more conversations around AI silicon and systems. AI with Sally is brought to you by Aspen Core Media. Thank you for listening.